Yes, thank you very much. So this talk is, as you just said, about shape-aware materials and how we can support interactive fabrication with a system that we built up called ShapeMe. I did this together with my advisors, Theophanis, Tsandilas, and Wendy, Mackay. So okay, I have some technical problems.
The last slide.
That is the last slide? Classic. So thank you for your attention and yes, indeed. So like the system that we implemented, you can see right here. So we have a material that a maker or an artist can model, and it automatically streams in real time a digital model of the changes that have been made physically. So the goal, or like what is the advantage of this, is that we want to support both physical and digital modeling. So physical modeling gives you many advantages. For example, you can use traditional crafting techniques. Artists can use their tools that they are most familiar with. Also, like, you directly get a response from the object that you create, so you get the stereoscopic vision, you can hold it into the light, you can see the shadows. But digital tools also have advantages that physical modeling cannot really support. For example, when you can explore symmetries by using the mirror tool, where you just have to work on one side of the object and the other side gets rendered automatically. Also, digital tools are very precise, they have a high speed, and the models that you create are lightweight because they're data, so you can just send them around, and you can have like a huge library of different models on your hard drive stored, which is really hard physically. So, and this is exactly where we wanted to support makers and artists with the system. So we have on the one hand the support of physical tools with the material that you can shape with physical tools, and also this digital model that gets streamed directly into a 3D CAD environment where you can then apply the digital tools to it. So this concept was for interest for HCI so far. So this mixing of digital and physical tools for prototyping. Like one stream of research goes into camera-based systems where you actually track the physical changes of an object and create a digital model from it. These systems are really great, but also like these camera-based systems have sometimes problems with occlusion when the person is working on it, and some parts may be hidden. Also, there are smart tools. They track the position of the tool, and then from this they compute the digital model. But these systems also have the problem that when you move the tool, you need to recalibrate and like look where the tool is to have a correct model. So like the first thing that we did, we wanted to like more understand actually how makers create objects and how they model with it. So the first thing we did was we did interviews with professional makers. So we were visiting a shoe manufactory where they produce shoes for people with special needs, so like very individual shoes. And one of the main challenges for them is to create the sole that consists of multiple layers. They are very similar, but each of them needs to be fabricated individually because it is this physical process. There is no copy-paste operation. Then for architects like use both digital models and physical models. Physical models are very often shown to communicate with a customer, for example. And also like here we see a layered approach. So they create layers, they shape them, then stack them on top of each other to create volumetric objects. We also did a workshop with novice makers. So we had 11 participants that had the task to create a gingerbread house with modeling materials. So we used foam core sheets. We started with a paper sketching stage or phase to create an initial idea, and then the prototyping with the foam core sheets. And you see here like a couple of outcomes from it. And we observed some techniques that people used. So on the one hand, this physical modeling was really helpful for them because they had individual pieces, they were there, and they could recombine them to explore a different and alternative solution. So it supported ideation. But on the other hand, when they did a mistake and they did like a wrong cut, it was like really hard to actually undo this operation. So they actually had to like refabricate these objects. So like these first explorations on how people model and where like the benefits and the disadvantages of like physical and digital modeling are, brought us to like what we actually wanted to implement, so our challenge. So we have here like these two parts. We want to support physical modeling and digital modeling. And what we need on the one hand is when we do physical modeling, we want to have this transition to a digital model. So we need some kind of a sensor technology that is able to capture all the changes that are made by the maker and create a digital model from it. And the second direction is, when you have now the digital model, we need to have some software toolkit that allows us to recreate the physical model that is again shape aware, so that can capture its own shape. So we will start now with the first part with the sensor technology and how this can be made. So the question is, how can we actually capture the shape of physical material and digitize it? So now imagine you have some cuttable foil. So like imagine this is a sheet of paper, yes? So this sheet of paper, we print a set of, like a grid of line-shaped sensors. How they're made, I will come later to it, but let's imagine this is the shape of these sensors. So when this sheet now gets cut, the sensors will be cut with them. So, and now, in the case that we would be able to determine for each one of these line sensors where this cut actually happened, then we would be able to combine like these cutting points and do an approximation and interpolation between these points, and by this we would get a digital model of the shape. So, and what we need for this is, since the position of each sensor is known, the only thing that we need now is we need to be able to measure the length of the sensor. So and with the position and the length of the sensor, we can compute the cutting point exactly. Yes. So the question is, like, how can we now sense the length? So we need a cuttable sensor that is able to sense the length. And our solution to this is the following. So again, like in the middle, this dielectric layer, imagine this is a sheet of paper, and you're looking at it now from the side. So you can see on the top electrode that we can print the top electrode that is on the top side of the paper, and the bottom electrode on the lower side of the paper. Yes. So and when these two electrodes are overlapping, what we actually then get is a capacitor system. So when we now apply on the bottom electrode an AC current, let's say of like 60 volt, what will happen for a capacitor is that you will get a reaction on the top electrode, and you will also get an AC current. These line sensors that we have are pretty small. So like the area is pretty small and the distance between the two plates is pretty small, which leads to the fact that they have very low capacitance, which on the other hand means that these 60 volts are not, it doesn't reach the same amount of voltage on the top electrode. It will be a little bit lower. So and now comes the trick to it. When we cut it, the area even gets smaller. And when the area gets smaller, the capacitance drops, and also with it, the voltage will drop. So coming from this voltage, we want to like recompute the length of this sensor. So, but now we need to have a mapping function that maps this voltage to the length. And for this, we did the technical evaluation. So you see here our setup. On the left side, you see 15 test sensors that all had a length of 250 millimeters. And on the right side, a set of reference sensors with different lengths. They started at 250 millimeters and then went to 0 and 25 millimeter steps. Also, we printed these sheets in two different sizes. So the width of one set of these sensors was 1 millimeter, and the second set of these sensors was 0.25 millimeters. And our procedure was that we were cutting the test sensors in 5 millimeter steps, and after each step we were measuring 100 times the voltage of each of these test sensors. So this is our outcome. So, and what you see here is, and this is like the main finding of this technical evaluation, there's a linear relationship between the length and the voltage. So when you cut the length of the sensor, also the voltage will drop in a linear fashion. We also like tried out with the width of the sensors to go down to 0.25 millimeters. What you can see here is there's a bit more noise, of course, because the capacitance is smaller, so we introduce more noise. With 1 millimeter, the sensing values were quite clear, and we could reach an accuracy with this mapping of on average of 2.5 millimeter. So now that we have these layers that are able to sense the shape, we want to now integrate it into modeling material that actually you can use it as a shape-aware modeling object. So, and the way how we do this is very straightforward actually. So we take these sensor layers and we apply them on a sheet of modeling material. This then is going for like plates, like these foam core plates that we had in this study before, and you can also extend it to volumetric objects in 3D by just sampling it, so by just stacking layers of sensors and modeling material on top of it. So now we talk about these grids of sensors. So what you saw in this and the structure that you, and like the question is of course like what kind of grids do we actually want to print? So in this initial example you saw this here. So we have there some specific topology of these sensors, and when a cut is made like this one, the reconstruction is actually pretty well with like a few small errors. However, there are also, this is an alternative example of a cut that is a little bit more problematic. So you see, like here on the left side, there are sensors cut off. So this is a challenge to the system, because when these sensors are broke, only the last point of the cut can actually be measured. So you see it here in this figure. These are the intersection points that would get measured by our system. And when you do an interpolation with it, you see that there's a problematic area that cannot be accurately captured. So we were suggesting for this a set of alternative sensor topologies. So you see here like a couple of examples, and these red lines are indicating what the ideal direction of a potential cut would be. So we have there the parallel line setup, which is optimized for more horizontal cuts that have like a roughly horizontal shape. We support structures that go more into the direction of peripheral cuts. And also our system with the last sensor topology is also supporting holes and vertical cuts. And a user can then, when there's some initial idea on what kind of cuts will be made, the user can then select the appropriate topology. So about the fabrication, like taken together with what I just showed about how the sensor technology works, we have the 3 layers. So we have the top layer, which contains the topology of the sensors, then an insulating layer, which is something cuttable, for example, paper or transparent foil. And also, when you remember, we need to have a lower, like a bottom electrode that is charged with an AC current. And for this, we don't need individual ones, but we can use one homogeneous conductive layer that gets just charged and is powering all the sensors on the top layer. The fabrication of each of these layers. For this, we use an inexpensive and rapid fabrication technology based on inkjet printing that prints conductive silver traces. With this technology, this is also commercially available. With this one, we print the top layer with all the detailed sensors. And for the back electrode, at the moment, we use screen printing of conductive polymer called P.PSS. But alternative solutions are possible. So if, for example, you can also spray some carbon-filled particles as long as it is conductive and is a homogeneous layer. So another challenge for the system is we want to have a high resolution in the shape reconstruction. And to get a high resolution, of course, the more sensors you have, the better it is. And this brings now the challenge of scalability. When you have to connect like 20, 30, or 64 sensors, like in this case, we need to have some hardware that's actually supporting a convenient way to connect them. And for this, we developed a ShapeMe board. It contains FPC connectors where you can just, it's a plug-and-play system. You can just put these connectors in and click, and then it is connected. And this enables makers to also connect larger and high-resolution shape sensing sheets. In the example that we saw before about these volumetric objects, that can also, like shape-aware material can also have multiple layers. And for this, we made the ShapeMe board also stackable, so you can even connect more of these boards together to sense even more sensors. So this was now the first direction about the sensor technology. The second direction, going from the digital model back to that makes the communication from the digital model also to a physical model, such that you can fabricate it and integrate the sensors. We developed a software toolkit that is supporting this. We call this the ShapeMe toolkit, and it is what you see here on the left side. So this software system is supporting the communication between the digital model and the physical model. So on the one hand, you can create initial shapes digitally in the ShapeMe design toolkit. It creates all the necessary layers and sensors which can then be fabricated in the way that I just presented. And on the other hand, when these sensors are active and there are physical changes made, it also collects all the voltage data, converts it into geometric data, and can send it to a 3D environment. We made plugins for Unity, so you can, for example, directly render it with Microsoft HoloLens, for example, or anything that supports Unity. Or we also have a plugin for Blender, which is more focused on this digital modeling aspect. So like now I will show you one application scenario about architectural modeling where you also will see in action how this toolkit and how the fabrication and the interaction with both the digital and physical works. So I'll imagine now there's an architecture student and she wants to make a building. So the first thing that she does is, and she wants to make it physical, she wants to design physically and wants to combine this digital and physical modeling. And what she does is she takes the design toolkit, selects the amount of layers, the layer thickness, and then when this is done, she goes to the templates and selects a template that suits her best. The toolkit automatically creates all the sensor topologies that she wants. She can customize the shape, the size of the entire sheet. It creates the wiring to the connections. You can select a topology of those that we have. And finally, these can then be exported into a PDF file that can then be sent to the inkjet printer for this silver inkjet printing, to the laser cutter to cut out the particular sheet. So when this is done, you can see here the setup. So on the bottom of this image, you see like an example of a fabricated layer. This one gets connected to a computer and to the ShapeMe toolkit. And the ShapeMe toolkit streams over OSC the geometric data directly on the left side to Blender, where this shape-aware object automatically gets created. The toolkit then does some calibration, and the architecture student can start designing now like digitally and now even physically. And all the changes that are made physically, are directly captured, and it can be then like reconstructed on with a laser cutter. So. And also, parts can be also designed digitally. For example, the roof of the house. It can be again with the toolkit fabricated, and small-scale details. For example, like adding details to the roof can be done physically. And now we see like an example where like a mistake has been made and like a large piece got cut away. So now we can use the history toolkit of the design kit, go to an earlier version, and refabricate it again. So we are tracking here the physical changes digitally. So, and in the second part, we want to create the terrain. This is now a multi-layer object, so a volumetric object. So we create multiple layers. We again fabricate it. Connected now with the ShapeMe toolkit that gets, with the ShapeMe board that gets stacked on top of each other. And the geometric data gets streamed directly to the digital model. And then these digital models of the house and of the terrain can be combined digitally again. So far, as a conclusion, what we wanted to achieve was this combination between physical and digital modeling. We showed a sensor technology that is able to capture the shape, and we showed a software design toolkit that manages the communication between the physical and the digital object and allows to fabricate these shape-aware materials with inkjet printing technologies and with personal fabrication tools. So this is the end of my talk. I thank you very much, and I'm happy if I can ask 2 questions.
Okay, while we're asking questions, I'm going to go ahead and ask Vikram to set up.
Hi, Danny Ashbrook, University of Copenhagen. This is really, really fun. So I'm wondering if you've thought if there's a possible architecture to enable you to do this like fully in 3 dimensions. So to actually sculpt something where you can have holes and parts cut apart and make an entire sculpture essentially that would be captured.
Yeah, of course. I would say this this is related a lot to the possible topologies that can be printed inside. So like one of our limitations that we have right now is that we have to layer it because there's not really a 3D printing technology for like printing these sensors like in 3D, which will help you a little bit. So, and this is definitely like one of the challenges that we would like to also like go into the future to like make a more high quality model of actually how we can print.
Yeah. Could you stack different topologies just right on top of each other with insulation in between?
So like there are 2 versions. On one hand, you can just use like one topology and use like many layers. Or what is also very interesting is combining them, because each of these topologies has an advantage in some kind of sense. But when you combine them, stack them on top of each other, you can increase the geometries that you can actually sense from it. Yeah.
Cool. Thank you.
Okay.
Hi, Sean Fulmer, Stanford University. Great talk, really exciting work. I'm wondering, my question is sort of towards a similar direction in terms of thinking about extending your work to like kirigami or origami. And I'm wondering if you've thought about how you might be able to use your sensor to detect more complex bends, and if there's a way to
Yes.
both sense cutting and bending at the same time.
So this is like a very interesting question, because I also have like a second demo today where we do actually something with origami, which is awesome. So like at the moment we're focusing on sensing the cut, so like to sense the shape change, so to say, of rigid objects. The next extension, of course, is when we talk about material properties, to go into flexibility and to stretchability and to also sense that. So we didn't do this so far because we were focusing more on this cuttability part, but an extension to it, that we also can sense deformations of the object. This would be definitely like a very, very interesting direction that I would be very into doing.
Okay, let's thank our speaker.